Today we'll be talking about population growth models, two of which are exponential and logistic. And so the difference between the two is that exponential growth is a growth rate that becomes more rapid in proportion to the growing total number or size of the population. And so it looks, both graphs have the same axes, population on the y-axis population and time on the x-axis. Now you can refer to time as the generations, and so the graphs look very distinct from one another. That's because exponential has a growth rate that looks like this, but then spikes upward. Oops, apologize, spikes up. And so this is due to unlimited resource and unlimited food space that an organism could have. So an example of an organism that has exponential growth, that exhibits exponential growth, is bacteria. And so this looks very distinct from logistic because logistic growth is limited due to resource constraints. So the graph of logistic growth looks a little bit like this, and then it starts to kind of plateau at a certain point. So there's a growth, there's a growth, there's a growth, there's growth over time in population, and then there's a plateau due to limited resources and limited space in which an organism can live. And so what this is called is a carrying capacity in which this graph reaches, which is K. And so in talking about variables and in terms of variables, I'll give you an example in which exponential growth has an it has an equation. And so the equation is dn over dt, which is the population size over time. And so that is equal to r times n, and r is a growth rate. And so we can kind of look at an example in which r is used, another equation. And so r, the growth rate, is equal to the number of births minus deaths divided by n, which, as we said before, is the population size. And we can use this example, these two equations, for an example. We can use an organism such as mice, and so we'll look at a table in which we can kind of compare numbers and get some results to have a graph to look exponential from a table. So we'll use time as one of our variables, which is x, and n, which is the population size. And so time, as mentioned before, can be measured in generations. So we'll look at generation 0, the starting generation, and then 1 and 2. And so we can kind of come up with a theoretical number of mice to start with, so I'll put 20. And so we can use the equation we had before, which is r equals to births minus deaths over population. So we have, let's say, 6 births minus 2 deaths in the population over 20. And that is equal to 0.2. Then we have our r. This is our r. This is our growth rate at which the mice grow. And so then we can multiply it times 20. We'll get 4. And so we add that number to our original size, n, and so we get 24 for the first generation. And we can see how this happens in the way that time population size grows slowly over time. And so if we apply the same equation to generation 2, we'll actually get 29. I hope this video helped. Thank you for watching.